Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated by their senior colleagues. Today, we have Elena Wang, who is a postdoctoral researcher at TU Graz. Elena will be speaking on comparing embedded graphs via the labeled merge tree distance. Take it away, Elena.
Thank you for the nice introduction, and thanks to the organizers for the opportunity to speak. So today, we're talking about comparing embedded graphs. But before we start with that, let me recap the typical topological data analysis pipeline, which is the field that I'm in, and the tool that we're going to be using comparing embedded graphs. So in topological data analysis, or TDA for short, usually we take an input data, and that can be an image, that can be scan, and we compute the topological signatures of that input data. We have a lot of choices in there, and then using the topological signature, we perform downstream analysis using tools from machine learning or statistics. Like the title suggested, today our input data is going to be embedded graphs. What is an embedded graph? So we're first and foremost given a typical graph consists of sets of vertices and edges. Embedded graph has a continuous function phi that maps the graph to the real space, and the function phi is homeomorphic onto its image. It's useful to compare embedded graphs in real-world data, as it can be used to classify neurons, for example, or we can use embedded graph comparisons to compare two reconstructed maps of the same city from different time periods to quantify how much the city has changed over the years, or we can use it to study protein functions. So today, the question we want to answer is, given two embedded graphs, how can we efficiently compare them? What we want to do is we want to capture the topology of the graph, and we want to capture the outer shape of the graph using topology, and we also want to make it computable in practice. So to do that, we choose merge tree to be our topological signature. Now, given a graph G on the left here, we have to fix the direction. So in this example, I fix the direction that points towards the North Pole. We can define a height function. By that, I mean all the vertices would have a assigned height value based on that height function. And we can construct a merge tree according to this graph and this direction of choice by sweeping a threshold that is perpendicular to the function from negative infinity to positive infinity. The intuition is that the merge tree will keep track of how the connected components of the graph behave as we sweep this threshold. Now, for example, we sweep from negative infinity, and here we encounter our first connected component of G. I generate my first leaf in my merge tree. And at this height, I pick up my second connected component, and now I have two branches in my merge tree corresponding to these two separate connected components. And these two components merge at this height. Now, on the way, we actually passed through a third vertex, but that didn't actually do anything to the merge tree because it didn't affect the number of connected components in our subgraph induced by this threshold, so that didn't change anything. And anything beyond this height, everything is one single connected component, so we have an infinite tail attached to the merge tree. So that's how we represent an embedded graph at a fixed direction using merge tree. Now, if I added labels to the merge tree, I can have a matrix representation of this tree. So how do I do that? We first have to ensure that all the leaves of the merge tree have to have a label, but that's the only requirement. The rest of the remaining vertices doesn't necessarily have to have one. So here I have three labeled vertices of my merge tree. How do I construct its induced matrix? We take for any matrix entry, we take the height of the lowest common ancestor of the two vertices that are labeled with the row and column index. That's a long sentence. Let's unpack that. Looking at this example here, we can first look at diagonal. Let's take entry 2, 2, for example. What we do is we find the vertices labeled 2 and 2, which is the same vertex, and it's at the bottom of the merge tree right here, and it has the height a0, and that's why a0 goes into the entry of 2, 2. And we do the same for the other diagonal entries of 1, 1, which gets the height of a3, and the entry 3, 3, which gets the height of a1. So what do we do with the off-diagonal entries? Let's take 2, 3, entry 2, 3, for example. I first find the vertex labeled 2, which is at the bottom. Sorry, I can't find my cursor on the screen, so hopefully you'll be able to follow my verbal cue of finding these labeled vertices. And so we find for entry 2, 3, we find the vertex that is labeled 2, as well as a vertex labeled 3. And for those two vertex, I have a vertex that is not labeled as their lowest common ancestor, but that's okay because I still have a height function, height information on that vertex, which is a2. And that's why a2 goes into the entry 2, 3. And by construction, we get a symmetric matrix. Now, if we're given two labeled merge trees that have the same sets of labels, I can have two induced matrices of the same size. Now, given that, I can take their difference matrix, and I can define the L infinity norm of that matrix, which is the maximum entry over all absolute values, to be the labeled merge tree distance. Right, in this example, all I did to get T2 was to move the merge point of vertices labeled 2 and 3 from the height A2 to A3. So naturally, that is the only entry that changed in my induced matrix. So when I take the difference between these two induced matrices and take the L infinity norm, naturally I get the absolute value of the difference between A3 and A2 to be my labeled merge tree distance. Now, this procedure naturally has a pitfall, which is the entry-wise sum of matrices require them to be the same size, but that's not guaranteed when we're just given a pair of embedded graphs, for example. Here in G1 in pink graph, I have 3 labeled vertices, and in the blue graph, I have 4. So how do we generate the same number of labels on each of those labeled merge trees? Before we do that, I have to introduce a concept which is called extremal vertices. Let's review the definition of convex hull, which is the polygon with the smallest boundary that encloses all the points and edges between any two of them. Then we define an extremal vertex to be a vertex that is not in the convex hull of its neighbors. Let's take a look at the example at the bottom, on the bottom left. Right, in this graph, I have 4 vertices, and if I just take the convex hull, that's a triangle. But if I just zoom in on the vertex that is labeled V1, I see a question pop up.
No worries.
Oh, okay. Thank you. I can't see I somehow lost my mouse, so I can't click on anything or correctly click on anything I want to. Okay, if no questions, and if you do have any questions, please feel free to unmute yourself and ask away. But if there's no questions, let me continue with this example. So if we zoom in on V1, it has 2 neighbors, which are the top 2 vertices, and the convex hull of these 2 points is just the edge, and V1 is not in the convex hull of neighbors, so it's an extremal vertex. And what's important about this set of vertices is that they give birth to a leaf in a merge tree for some directions. And it's an if and only if condition. Right, so for example, V1, if I take the same direction that points towards the North Pole, I get a leaf that's generated by V1. However, if I do a small modification, which is connecting V1 to the bottom vertex, Now the neighbors of this vertex becomes the whole triangle, and then V2 is then contained in the convex hull of its neighbors. And from the same angle, actually from any angle, V2 doesn't generate a leaf in the merge tree from any direction anymore. Great, so that's actually the set of vertices that we care about in terms of labeling, because we only need to guarantee that the leaves have to be labeled. So what we do is, given a vertex, given an extremal vertex, we find the closest point on the other graph. So in G1, the point of choice in this example is V1. So the point on the top here, and its closest point on G2 is the P1 that I added on the blue graph. And we can add a node on the merge tree that's associated with it, which means that at the given direction of computing, we can just add a point that have the same height value. Now, if we do that for all the extremal vertices, then I'm guaranteed to have two labeled merge trees of the same size. And following that, we can compute the induced matrices. They're going to be the same size again, and therefore we can compute their labeled merge tree distance. Is there any questions? All right, if not, another thing that we had to pick when we generate the merge tree was actually the angle of which we're computing it from. All right, so here, for example, if I pick omega-1, so I sweep my threshold from left to right, more or less, I get just one single connected component throughout. So I get only one branch in my merge tree. If I rotate omega-1 counterclockwise to omega-2, for example, so we sweep our threshold from kind of bottom to top, there we get a merge tree that has two connected components, or two leaves, two branches. So that's why it's important to take the information of the graph into account by sweeping the whole circle, and that's what we call directional transform. So we end up computing the merge trees from all, well, we want to compute the merge trees from all angles, but that can be expensive. So it's important to identify which angles are important to us, i.e. between which pairs of angles does the change happen only minimally to our merge tree. And these angles are actually the normal vectors of the edges. The normal vectors of edges are what we call the critical angles. These are the angles at which the combinatorial structures of the tree could change. In this example, the critical angles are marked by the blue arrows. We notice that these are actually a superset of angles where the combinatorial structure can change. But the combinatorial changes can only happen at a critical angle. Now, putting everything together, we actually have our labeled merge tree distance. So we compute our labeled, given a set of graphs, we compute their labeled merge trees and therefore their labeled merge tree distance from every single angle to obtain a distance graph that ranges from 0 to 2 pi. And we take its integration to be our labeled merge tree transform distance. And the main theorem of our paper states that this height function is actually continuous. And this continuity will help us a lot in the next step, which is implementation. So here, let's summarize the steps of the distance construction, as well as the step that we follow to implement it. Given two graphs, G1 and G2, we first create their labeling schemes just by generate labels for all extremal vertices. We then compute a set of critical angles, which is the union of the angles that are normal vectors to all the edge sets of the two graphs. And these are what we call key angles. Apologies. The angles between any two pairs of neighboring critical angles is what we call key angles. And then we build merge trees at each of these key angles. And these are stored as the information of the merge trees is then just stored as the lowest common ancestor matrices. And then we can compute our piecewise continuous function. Well, the naive way would be just to sample them. But we can also do something smarter. which if I have time, I'll expand on later, which we utilize the continuity nature of the function to construct a kinetic data structure to compute this piecewise continuous function. And at the end, we can integrate the discretized infinity norm distance to obtain our final distance. All right, so following these steps to implement it, we want to actually test to see if this distance gives me something meaningful, i.e., can it differentiate the differences between two embedded graphs? So we used it on two data sets. The first one is a data set consists of more than 3,000 Passiflora leaves of 40 different species. Now, each data point consists of 15 cross-aligned XY coordinate pairs representing 15 landmarks on each leaf. So each data point is a graph that looks like something on the bottom left here, which is the outline of a leaf generated by these 15 landmarks. Well, if we had connected all the landmarks, we actually get some internal vine structures. However, those vine structures are naturally ignored by the merge tree construction. So when we tested our distance, we removed those internal edges. So the goal is, of course, to see if our LMTT can be useful in differentiating each of these classes. Let's zoom in on a pair of examples. So what I did here is I took two pairs of leaves. On the first row, on the top row, I took two leaves from the same species, and on the bottom row, I took two leaves from different species. So naturally, what we wanted to see is the distance for the top row much greater than the distance between the two leaves on the bottom row? And the answer is yes, right? If we just, well, we have the distance graph is normalized to the min and max, so we have to pay attention to the y-axis. But we can already tell from the distance graph here, as an example, that the distance between the two leaves on the top row is much smaller than the distance between the two leaves on the bottom row. Now we do that for every single pair of 432 sampled leaves. And that's how we constructed a distance matrix using our LMTT. And we fed that through a multidimensional scaling process to visualize the pairwise relationship. And the graph, the figure on the left, is what we got from our MDS scaling embedding using our topologically informed distance. So what this tells us is that if 2 points are close together in this embedding, that means they're similar in shape using our distance. So we can see that for classes that are inherently much more different than others, like for example, classes of A through D, they're quite well separated using LMTT, while the classes that are similar to each other are clustered closer together. We also compare that to a PCA analysis that just took the 15 coordinates and see where the two principal components lies. And we do see that LMTT outperforms the PCA in terms of how close the clusters are visualized together. The second data set we tested on was a handwritten letter data set. So this data set consists of 300 graphs generated from handwritten letters. These graphs are not isomorphic anymore, meaning we have different numbers of vertices and edges. And here we actually see even clear clusterings across different letters. And we can pay close attention to the two clusters H and X that are close to each other. This makes sense because if we think of our merge tree construction and topologically H and X are actually very similar to each other, especially in a handwritten setting. However, our distance does come with its limitations. One is that it eliminates internal structure, and that's by choice. However, the second one is that the labeling scheme is quite volatile in that if I moved a graph a little bit, the label can end up in drastically different place of the other graph. So in our future work, we're trying to improve on this kind of unstable nature of our labeling scheme. Our current work also focuses on comparing this distance with other topologically informed distance, but I think my 20 minutes is up. So I would like to end with a thank you to the audience and my collaborators, Erin, Liz, and Sarah. And this paper is going to appear on La Mathematica, and it's available on arXiv right now. Thank you very much.
All right. Thanks to our speaker. I'm going to thank her by clicking this react button and doing one of these